Now we are going to talk about magnetic force. So, you children, I hope you have played with magnets in your childhood. Okay. So when you bring two magnets, generally what happen? Either they may attract or they repel. Yes, isn't it? Generally, when we talk about poles of the magnet, we speak only these two poles, either north pole and south pole, right? A magnet has two poles, north pole and south pole. So why does a magnet has only north and south pole? Why don't they have east, west and some other poles? What is the reason? What is the reason behind that? So the reason behind that, I'll explain. You take one bar magnet. Let's say this bar magnet has a north pole and a south pole. This bar magnet is suspended with the help of a thread which is attached to this. Okay, so we have connected this thread exactly in the middle of the magnet, so it is able to suspend horizontally. It is not tilting. So without tilting like this, okay, without tilting, we have to make this horizontal like this. We have to suspend in a way. Okay, whenever you suspend this magnet in the air, this magnet always shows north direction and south direction, east, west, north, south. Let me say, towards my left hand east, towards my right hand west, my back side towards board north. Okay, now opposite to the board south. These are the directions. So let's say this is a magnet. I am suspending this magnet. So this magnet always comes this way, north pole and south pole. Okay, it never changes direction this way, east and west. It always comes to rest, showing the north direction and south direction. What is the reason behind this? Because our earth is also a big magnet. It also has a magnetic field. It also has two magnetic poles. Okay, so generally these are the directions we say: east, west, north, south. These are the directions generally we denote on the board while drawing the diagrams. Okay, engineering drawings. So generally direction is denoted this way. This is our geometrical north and this is our geometrical south. Our north is this towards board. Okay, east is towards my left, west is towards my right, south is towards you. That means opposite to the board, right? Towards board we have north pole, right? Okay, north direction. But earth has south pole towards the gravitation, towards the geometrical north. So this is the north pole. Generally this is the north direction and towards you south direction. Opposite to the board is south direction. But under the earth also has two magnetic poles, north pole and south pole. But under the earth, towards north side earth has south pole, towards south side earth has a north pole. Now I will make it clear. So this is the geometrical north direction and this is the geometrical south direction. Geometrical north direction earth has the south pole, geometrical south direction earth has the north pole. That is why when we suspend a bar magnet, the north pole of the bar magnet is attracted by the south pole of the earth. The south pole of the bar magnet is attracted by the north pole of the earth. That is why this suspended magnet come to rest, showing the north and south. Even though if I change the directions, I will keep the south here and the north here. I will change the direction and I keep this way. Then what happen? Again, this magnet rotates this way and finally comes to rest, showing the north and south only. Why? What happen? If you change the directions, south and north, between south and south, there is a repulsion. Between the north and north, there is a repulsion because same poles repel each other. Due to the repulsion, again this magnet turns and finally comes to rest with showing the north pole and south pole this. I hope you understand the reason. When we suspend any magnet, it shows north and south. Okay? So because geometrical north side our earth has the south pole, geometrical south side our earth has the north pole. So due to the attraction between the south pole and the north pole and south pole, so that comes to rest, showing north and south direction. Okay, and this basic thing also I hope you know. If I break this magnet into two pieces, this magnet divided into two pieces, and this magnet has north pole and south pole, this piece also has north pole and south. Like that you break this magnet into n number of pieces. Okay, even you take small pieces, a small piece, and that small piece also has north pole and south pole. So magnet never exists with a single pole, it always exists with a dipole. two poles, North Pole and South. North and north like poles, south and south like poles repel each other, unlike poles attract each other. When this magnet brought near any magnetic material, what is the magnetic material? The materials which attracted by the magnet are called magnetic materials. So what are the magnetic materials? Example, iron, steel, nickel. These are some examples of magnetic material. Again, in magnetic material there are three types: dia, para, ferro, but I don't want to discuss that concept right now. Okay, that we discuss in magnetism chapter in introduction part. So these are the best examples of magnetic material. When you bring a magnet near these pieces, these materials attracted by the magnet. Okay, but this plastic, rubber, okay, wood, dry wood, such kind of bodies, do they attract by magnet? No, they are called non-magnetic materials. So materials which attracted by magnet are called magnetic materials. Materials which do not attracted by the magnet are called non-magnetic material. So from this basic thing, what we can understand, how can we write the magnetic force? Okay, so magnetic force is the force exerted by the magnet. Force exerted by magnet is called a magnetic force. Now more about magnetic field, magnetic force lines, now we are going to discuss. Okay children, now we are going to do an experiment to understand magnetic force. Okay, this is coin. It is ferromagnetic substance. There are three different magnetic substances: dia, para, ferro, what we have discussed in the video. This is made of ferromagnetic substance. Okay, this is iron, safety pin. What is this? It is a safety pin. Okay, this is safety pin. Okay, it is made of iron. And this is magnet. It is not the natural magnet, it is the artificial magnet. It is prepared. Okay, it is prepared by ferromagnetic substance. It's a steel. What is this? It's a steel, right? It's a magnet. You see, you will understand. I keep one magnet here. Okay, okay, so this is one bar magnet. Here we have one bar magnet. First I am going to bring this coin very close to the safety pin. Okay, can this coin attract the safety pin initially? No, this coin is unable to attract the safety pin. But if I keep the coin this way, and when I bring this coin near the safety pin, what happens? It attracts, right? Isn't it? Okay, now what do I do? I just try to remove this magnet. You see, I removed the magnet, but even the coin attracts safety pin. What is the reason? How long this coin can attract that safety pin? Until or unless we hit and we beat, this coin act like a magnet. Previously you have seen coin doesn't attract the safety pin, but now it is attracting because this coin is changed into magnet due to magnetization. So how does this happen? I'll explain in the video. Okay, I hope you understand this small activity. If you are interested, you can do this activity at home also. I explain what is the phenomenon involved in this video so that you will understand clearly. I hope you have seen previous experiment. What we have taken one coin, okay, and there is a safety pin below the coin. There is a safety pin below the coin, right? So initially this coin and a safety pin do not attract each other, okay, but when we kept a magnet, bar magnet on the coin, then this coin able to attract the safety pin. Even though when we remove the magnet, this coin able to attract the safety pin for long time. That just now you have seen that. Yes. So how is it possible? What is the reason behind that? I'll explain. So previously, when this is a coin, when this is a bar magnet, when we don't keep this bar magnet on this coin doesn't attract the safety pin. Safety pin falls. Even if you touch the safety pin with the coin, it falls. What is the reason? So coin is a ferromagnetic substance. Okay, coin is a ferromagnetic material. Ferromagnetic materials are the good materials with which we can prepare the permanent magnets. Now the magnets which I shown in this video, they are ferromagnetic material. Okay, so magnetic materials are three types: dia, para, ferro. Ferromagnetic materials are strongly attracted by the magnets. Paramagnetic materials are slightly attracted by the magnets. Example, aluminum and oxygen gas. And the diamagnetic materials, they always repelled by the magnets. Okay, so here we are talking about ferromagnetic substances. Okay, so magnetic materials especially are divided into three categories. One is a dia, another one is a para, and the third one is ferro. So in this experiment, the magnets which we have used, actually they are not the natural magnets which are available under the Earth's crust. They are actually man-made, they are artificial, they are ferromagnetic materials. Ferromagnetic materials have a special property. That property is called retentivity. Due to this retentivity, these magnetic materials, once they are magnetized, they permanently behaves as magnet. The best example just now you have seen. The coin never attract the safety pin itself. Coin is ferromagnetic substance. It's a magnetic substance, not the magnet. But whenever this magnet brought into contact with this coin, now this coin able to attract the safety pin. Even though we remove this bar magnet, this coin able to attract the safety pin for a long time. So what is the reason behind this? So to understand that, you have to understand the domain theory which is proposed by the Weber. Let's say I will divide this coin into three parts, three regions, this way. Okay, so in this region all the magnetic particles looks this way. In this region magnetic particles looks this way, same direction. In this region this way. So what is this arrow mark indicate? This arrow mark indicate it's a magnetic particle. So the starting one is the north and this arrow mark is the south. Then what happened when we bring, for example, this is the north pole and the south pole of the bar magnet. When the south pole of the bar magnet is in contact with this coin, all the magnetic particles, this arrow mark indicates all the magnetic south pole, right? Then all the magnetic south poles comes towards down, because south and south repel each other, north and south attract each other. Then all the north poles of this magnet is attracted by the south pole of the magnet. Then all the particles changes their direction this way. You see, previously the direction of the magnetic particles in different domains, different regions is different. But coming to secondary, when we kept the magnet, then all the particles align, arrange into one direction. Now this coin act like a magnet. Why it is act like a magnet? Because all the particles are arranged into, set into one order, set into an order. So particles are in order. That is why it act like a magnet. How long it act like a magnet? Until the particles disturb. If the until again particles change it into in order, this coin continuously act like a magnet. But when this is happen, when we beat it, when we heat it, okay, it will happen. But until or unless we don't beat, we don't heat, the particles once which are changed, once which are aligned, they be in the same state for a long time. This property is called retentivity. Ferromagnetic materials have this special character. Due to this special character, permanent magnets are prepared. Okay, so just you have seen the video, right? This coin able to hold the safety pin for a long time. What is the reason? This is the reason. Okay, right. So I hope you understand. The force exerted by the magnet is called magnetic material. Sir, when we kept the bar magnet on the coin, why all these particles are changed into one direction? Already I told you, this starting point of the arrow is tail is north pole and the starting part of the arrow is south pole. So if particles arrange this way, this is a south pole and this is a north pole, south and south, do they attract each other? No. That is why particles arrange this way. All the north poles are attracted by the south pole of the magnet. That is why all the particles are arranged this way. And this magnet has magnetic field. What is a magnetic field? So if you consider the magnet, this is a bar magnet. Okay. So have you ever played with magnets? Yes. When you played with magnets, when you bring two magnets very close and when you do like this, you feel some force exerted on your fingers. Have you ever feel the force exerted on your fingers when you play with magnets like this? Yes. What is the reason for that force? The reason for that force is magnetic field. See, so what is magnetic field? A magnetic field consists of force lines. That force lines are not visible to us. For example, this is a magnet. Around this magnet, force lines exist in three-dimensionally, but we don't know. We cannot see those force lines with our naked eye. Okay, but we can see the force lines with one experiment. I will show you that experiment. Okay, we are going to understand what is a magnetic field. Okay, see, this is the bar magnet. Now I am going to place the bar magnet over the paper, on the paper. Now I am going to place one paper over the surface of the magnet. Now paper cover the magnet. So I am going to sprinkle the iron filings. What are called iron filings? When you rub this magnet in the ground, small particles attracts this. Small particles are attracted by this magnet. Those small particles are called iron filings. Okay, now we are going to add those iron filings. When I add these iron filings on this surface, you see one particular pattern you will identify. Are you able to see this pattern? See what all these are? These are all force lines. What all these are? These are force lines. Okay, so force lines travel from North Pole to South Pole in all the directions. All the directions in the sense, how do you understand? If this is the magnet, force lines travel from north to south this way, this way, in 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 this way, here, like a globe. From north to south in all the directions, these magnetic force lines travel, and inside they are moving from south to north. Outside they are moving from north to south. So these force lines directly we cannot see. These force lines are not visible, but now these force lines we can understand with the help of these iron fillings. When we sprinkle the iron fillings on the paper, all the iron fillings arrange in a particular pattern. Okay, so this pattern refers magnetic field. So magnets are surrounded by magnetic field. This is a magnetic field, and all these lines are called magnetic force lines. Here you see, near the poles we will find the more iron filings. Okay, so here iron filings are more near the poles. Why? Here the strength is more. Okay, so where is the density? More density of the force lines present, their strength is more. Here strength is less. You see there are no iron filings in the middle of the bar. Okay, but you see the end of the bars, there are more iron filings because strength is more at the poles only, because the density of the force lines is more. That is why the strength of the magnet is also more. Okay, so this is magnetic field. A magnet surrounded by the magnetic field, a charge surrounded by the electric field, a mass surrounded by the gravitational field. Okay, I hope you understand what is magnetic field, how is magnetic field. Okay. Okay, children, I hope you have seen this experiment is just now magnetic field. Okay, how are the particles arranged? All the particles are arranged in this particular shape, right? This is the shape. So particles align this way. So magnetic force lines always move from North Pole to South Pole. Outside, they move from North Pole to South Pole. Inside, they are moving from South Pole to North Pole. See, these are not the open lines. Actually, these are connected this way. And these are connected this way. And some other connected from down. So if this is a magnet, force lines this way, this way, this way, this way. Three-dimensionally from north to south, all the force lines travel continuously in this manner. Okay, and from south to north, inside they are moving from south to north. The field is exists around the magnet, but we cannot see. But to understand that, just now, I will show you one video. I hope you have seen in that video. So this is a magnetic field. A magnet surrounded by the magnetic field. A charge surrounded by the electric field. A mass surrounded by the gravitational field. So this magnetic force, electrostatic force, gravitational force, all these are non-contact forces. Okay. So with the help of previous experiment, you understand the magnetic field. So these are all called force lines. What all these are called? Force lines. Okay. Do this magnet has the strength, the same strength everywhere? No. You see here, if you imagine one area here and here, I will draw the area with the blue mark. You see, we have imagined the same area, but in this area, more number of force lines are passing through this area. This is the area. From this area, force lines are crossing through this area. Here more force lines are crossing through this area. Here density of the force lines is more, but here you see only two lines are passing. Only two force lines are passing through this area. Through this area there are many force lines are passing. So here density is more. Where the density of the force lines is more, there the strength is more. Where the density of the force lines is less, there the strength is less. So this magnet doesn't have the uniform strength everywhere. At the poles the strength is more, and in the remaining areas the strength changes depends on the magnetic force lines crossing through the area. But you have to remember, this magnet has strength, more strength at the poles, because here density of the force lines is more. That is why it has more strength at the poles. And also in the previous video you have observed more iron filings near the North Pole and South Pole only we found. Very less iron filings we find around the other area of the magnet. But the area where North and South Pole exist, there we find many number of iron filings, because strength is more at the poles. That is why more iron filings attracted at North and South Pole. Okay, so bar magnet doesn't have the uniform strength. The strength is different at different areas. Okay, right. I hope you understood the non-contact forces. Okay, in the coming video, in the next video, we'll talk about contact forces, friction, muscular force, normal force. Okay, and more. Okay, I hope you are enjoying the videos. Please note down these videos. You have to refer these videos. Whatever the important notes I'm giving, you have to note down them so that it help you, okay, for better understanding of the coming concepts, right? Thank you, children. Have a nice day.